Welcome to the Explainer. Today we're diving straight into Lecture 8, Feature Selection and Dimensionality Reduction. We are going to solve the mystery of why having way too much data can actually ruin your machine learning models. We usually assume more information is always better, right? But in data science, that instinct can actually lead us straight into a trap.
Okay, let's quickly map out our roadmap for separating the useful signal from all that irrelevant noise. We're going to cover Section 1, the curse of dimensionality. Section 2, univariate feature selection. Section 3, recursive feature elimination. And finally, Section 4, principal component analysis.
All right, Section 1, the curse of dimensionality. Let's tackle the core problem every single data scientist faces before any meaningful machine learning can even get off the ground.
So, is more data always better? It is super tempting to think that giving a model more information will automatically make it smarter, but we really need to challenge that assumption. When we're building predictive models, it feels totally natural to just throw every single variable we have into the mix, right? Age, location, transaction history, the whole shebang, just hoping the algorithm will somehow figure it all out. But does it really?
Take a look at the peak of this curve here. It perfectly illustrates what we call the curse of dimensionality, which is also known as the Hughes phenomenon. Notice how the performance shoots upward initially as we start adding relevant features. But look closely at that dotted line marking the optimal threshold. The absolute second we cross it, we are just adding noise. The model gets completely confused by the irrelevant data, and predictive accuracy literally just collapses. So how do we fight this curse? Well, we use feature selection. Think of it kind of like pruning a tree so it can grow stronger. We intentionally reduce our inputs to prevent overfitting. And overfitting basically happens when a model just memorizes random noise in your training data instead of actually learning the true underlying patterns. By consciously stripping away all the fluff, we drastically cut down our computing time. We boost our model's true predictive accuracy, and, as a huge bonus, we make the final results much easier for a human to interpret.
Moving right along to Section 2, Univariate Feature Selection. Let's check out our most straightforward tool for cutting down our data.
Now, this process is highly systematic. We evaluate every single independent feature against our target variable just to see if it holds a strong mathematical relationship. We aren't looking at how the features interact with each other just yet. We're literally just putting them in a lineup one by one. We run statistical tests on each one to generate a p-value. If that p-value is lower than our chosen significance level, which we call alpha, then boom, the feature passes the test.
And this visually breaks down that final step. Notice those green check marks next to variables x2 and x4? They have really nice low p-values of 0.03 and 0.04, which clearly demonstrates a mathematically significant relationship with the target. Meanwhile, x1 and xn, they have massive p-values. They're just pure noise, so we ruthlessly drop them entirely.
But here's the crucial point. You can't just use a master key for every single lock. Your statistical test depends heavily on the type of data you have. Predicting a category? The chi-squared test is going to be your best friend for measuring association. Dealing with continuous numbers, an F-test comparing variances is definitely the way to go. If you're using practical tools like scikit-learn, this just means calling specifically designed functions like f-regression for your numbers or f-classif for your categories.
Okay, on to Section 3, Recursive Feature Elimination. Let's see how our toolkit evolves when we take a more iterative approach.
Instead of just looking at features in total isolation, RFE, or recursive feature elimination, is a recursive process that whittles away the weak links step by step. You see, univariate selection is incredibly fast, but it kind of ignores the reality that some features only become valuable when they're paired up with others. RFE solves this by evaluating how features actually perform together inside the machine learning model.
If you follow the arrows in this iterative loop, you'll see how it works. The model selects a combination of features and runs a test to check the accuracy. If the performance drops, those features get kicked to the curb. If accuracy holds steady or improves, that combination stays and the loop repeats. It systematically trims the fat until only the absolute most critical, synergistic features remain.
Finally, that brings us to Section 4, Principal Component Analysis. This is our most transformative tool for dimensionality reduction.
Now, PCA doesn't just eliminate data, it actually compresses it into summary indices called principal components, which are basically linear combinations of your original variables. Imagine taking 10 different measurements of a house, right? Square footage, number of rooms, length of the hallway, size of the backyard. and mathematically blending them all into a single, brand new metric that somehow captures 90% of the information from those 10 original variables. That is the absolute magic of principal component analysis.
So when you're literally drowning in a vast sea of highly correlated data, PCA simplifies the board so you can actually spot the hidden patterns. If you have a dataset with 100 variables that all loosely measure the exact same underlying trend, your model is going to really struggle to process that redundancy. PCA basically slices through that correlation, distilling it down into just 2 or 3 entirely uncorrelated dimensions. This lets you easily plot the data on a graph and visually recognize exactly what is happening.
To make this a bit more concrete, the very first step of PCA is finding the center of the data. We take every single data point, like x1 and x2, and we subtract the mean. This perfectly anchors our entire dataset right around 0 on a graph. This mathematical alignment is an absolute prerequisite before we can even think about blending any variables together.
Alright, so after centering, PCA projects vectors to figure out exactly where the data is most spread out. That direction of maximum spread, that becomes our very first principal component. We use what are called eigenvectors to map out the mathematical direction, and eigenvalues to tell us exactly how much of our original information is captured. I know it sounds highly complex, but honestly, it's really just about finding the best possible angles to view our data.
But look, data science is essentially the art of compromise, isn't it? Dimension reduction forces a pretty strict trade-off where you gain incredible accuracy, but you lose the ability to easily interpret what the original features meant. Because PCA literally mashes your original variables together into brand new mathematical dimensions, you can no longer point to an input and say, oh, this represents a person's age. The model becomes highly robust and lightning fast, for sure, but the inner workings become completely abstracted away from human logic.
So, as you consider the tools to fight the curse of dimensionality, always remember that trade-off. If you're predicting medical diagnoses, doctors demand to know exactly why a model made a specific decision, meaning PCA's abstraction might fail you completely in that scenario. But say for automated high-frequency trading where fractions of a second matter, that black box accuracy is absolutely everything. So I'll leave you with this question for the next time you're building a model. When exactly does the cost of a black box outweigh the benefit of perfect accuracy? Think about it.